next lecture, I'm going to discuss advanced models of MINLO in power systems. And advanced here means that these slides were completed at 8 a.m. this morning, or just before 8 a.m. this morning. So this is how advanced they are. Well, that's how long it took me to catch up with everybody else. So I'll discuss a little bit the challenges in these AC alternating current power flow equations. And then there has been a lot of work over the last decade or so on convex relaxations of AC power flow equations. And that's very interesting because they might allow us to get global solutions for reasonable sized problems. And then at the end, I just have some little bit of results on the geomagnetic induced current blocker placement problem that we were solving at Argonne that shows why this is a very challenging problem to solve. Okay, so here's just a reminder of the AC power flow equations in rectangular form. So there are these three sets of equations that have to hold at every bus or every node in the power grid. And they're defined over the sets of buses or nodes and lines L. And the variables are here in blue, and the first thing you notice is that you have a lot of multilinear terms there in these equations. And you have a quadratic equation at the bottom. So those are nonlinear expressions in general. And so the challenges are that you have typically a non-convex feasible set. And whenever you have a non-convex feasible set, so here's an example, very simple example of a non-convex feasible set, then even if you're minimizing a linear function, you have potential for multiple local optimizers. So if I draw a linear lines here, then there are certainly two. There's a local optimizer here, and there's another local optimizer here, or global optimizer over there. And so even minimizing an affine function of a non-convex set gives you many local minima. And this is a very simple non-convex set. The linearizations that I introduced in the last lecture, the DC direct current approximations, are not really useful for planning or if the topology of your network changes. So in situations where it's critical to get good solutions because you have cascading failures, these DC approximations are probably not the right thing to do. And solvers will most likely produce locally optimal solution that could be misleading in some of the questions that you're looking for to answer. So there's a very good survey by Daniel Molzahn and his advisor on AC power flow, and I've taken these pictures out of their survey paper. So there's a 3-bus system on the left here, and it's an illustration of the feasible set that sort of loops back around itself. So the surface, the colorful surface that you see there is the feasible set. So this is a very complex feasible set. And on the right is a 9-bus system. So those are very small systems. Remember, the US power grid will have something like 100,000 lines. So this is a very tiny system. And the feasible set here are these 3 conic shapes that are sort of separated by this ball that's cut out around the middle. And so there are a lot of local solutions and only one global solutions. And so the feasible space isn't even connected. Even if you had an algorithm that would stay within the same feasible set, once you land in the wrong feasible set or in the wrong part of the feasible set, it's very hard to get to another part. So the question then is, how can we overcome this? And one answer to this is to derive convex relaxations. Another would be to derive approximations. So we talked, for example, about piecewise linear approximations. The difficulty with approximations is that they're not accurate and that they may result in slight errors. Whereas convex relaxations at least give you guarantees that you're enclosing the feasible set. So a convex relaxation of this feasible set would be a circle, for example. But they might be very large. The relaxation might be very large. Okay, so here's just, again, the first relaxation that I'm going to show you is Shor's relaxation for the AC power flow equation, and it's derived for the rectangular form of the AC power flow equations. So notice on the left-hand side, we don't need to worry about anything. Those are linear expressions, while on the right-hand side, we have these bilinear terms. So all the terms are there. If you look very carefully, you multiply them out, they're all bilinear terms that involve either VDI or VDK or VQK and VQI. There's a VQI there. And so one way to construct a convex relaxation is to collect all these variables that are non-convex, that give rise to non-convexity in one big vector. And I'm not going to tell you how to do this, but there's a way of deriving new data matrices. But this will become apparent once you see the problem on the next page. So the first thing we're going to do is we're going to take the variables, the subset of the variables that appear in these bilinear expressions, and just stack them up into a single vector x. And so there's my single vector x, and there's some additional data that I need to construct, but that I can easily construct. And so this is the key idea or fundamental idea of SDP, or semi-definite programming relaxation. So I should have spelled this out. Let me write this here. So you construct a matrix by forming a rank 1 outer product of all your variables. So the x, remember, that's the collection of all these variables that appear in these bilinear terms. And you form an x transpose, that's a rank 1 outer product. And you call this matrix W. You give it a name. You can call it anything you like. And then you will be left with one non-convexity, which will be this equation here, which is still these bilinear terms. But you can relax that by observing that rank 1 matrices are positive semi-definite. And so you relax this inequality, or this equation, to this inequality here, that W is positive semi-definite, and you throw away the x variables. So that you get a semi-definite relaxation by rewriting all my equations in terms of W, and then using the trace to sum up and then relax the equation that I have, the one non-convex equation, to this inequality. And so why does this work? Well, if you form this outer product that I have up there, so if my x is given up there, and if I form x transposed, then this matrix, the first term is a VD1 squared, and then I have a VD1, VD2, and so on. So I will have all the possible bilinear terms, all the possible bilinear combinations that are in this vector x, and in particular, I have all the bilinear terms that I need to reconstruct my equation here. So whenever I find one of these bilinear terms there, VDI times VDK, I replace it somewhere in here. There will be a VDI VDK. And so this corresponds to some W, I don't know, LM. So there's some entry WLM, and I just replace it by that. That's all I do. And you can see that when I do that, then all these terms become linear expressions in W, because all the bilinear terms, there is somewhere in this matrix, there's a home for all these bilinear terms, and so all my bilinear terms become linear expressions. So the right-hand side of these equations is now also linear, and I can write that then in a convenient way of doing a matrix product with W that picks out the right elements and then taking the trace of this matrix product. So that's a convenient way of writing this down. And the data matrices are just constructed by figuring out what the summation was that you did on the previous slide. So that's how you'd construct these data matrices. So once you do that, I think on a small example, it's easy to see how you construct these data matrices. Okay, so this is really cool because now you have a set of constraints that are all linear. So all my constraints here are linear because trace is a linear operator. Everything in this equation is linear. The remainder of the equations that I showed you also were linear, so everything is now linearized in the optimal power flow equations. And the only thing that you have to worry about is the semi-definite constraint. So this constraint that says the matrix W is positive semi-definite, meaning all its eigenvalues are non-negative. And there are solvers for this, so there's SDP, semi-definite programming solvers, but unfortunately they're not really scalable. There've been a lot of progress, but the complexity of these solvers is still prohibitive for doing large systems. The nice thing is that if you get a W, so if this W that you get out actually has rank 1, then that means you can write it as an outer product. So if W, so if the rank of W is equal to 1, then it follows that there exists some vector little w such that big W is W transpose, and you can reconstruct your x variables out of this potentially. Unfortunately, well, any good idea, somebody comes up with a counterexample. So there exists a small counterexample where the rank of W is greater than 1. So it's not solved. The relaxation is not exact. And in fact, there's a practical example from the French power grid with a very large optimality gap. And so the optimality gap here means that if I look at this picture, the optimal solution in my non-convex set would be here. The optimal solution in my relaxation would lie out here. So this is a small optimality gap between these two numbers, but in this system it's a much larger gap. And that's probably not surprising because these sets are sort of forming and turning around on each other. And there's a lot of empty space in these sets. And if you now convexify them, then this empty space will allow solutions that could be very far away from the true optimal solution. So this is, based on this, there's another set of relaxations, and this is Jaber's second order cone relaxation. So this is derived for a different system in polar form. So I said there are three different ways, at least three different ways for writing down the power flow equations. So here's another way of writing down the power flow equations in terms of polar coordinates, the VI magnitudes, and the voltage angles theta I. So the phasor V is expressed as here as the voltage magnitude times E to the I theta I. That's my voltage phasor here, one that I start off with. And if you look at this, and if you're smart like this person, then you realize that you can write this as a second order cone formulation if you make the following substitution. So introduce new variable CIK, which corresponds to products of VI, VK with cosine. And similar in SIK, which corresponds to these variables here. And so if you do that, then you get a relaxation. If you look at this CIK here now, in my voltage equations, that will be replacing the top left term there. That will be replaced by CIK times GIK. The second term would be replaced by minus SIK times BIK. So this is now a linear set of equations, if I do this little trick. There's one non-convexity left that I didn't put there, and I forgot, but we'll see it on the next page. And the one convexity that's left is this voltage magnitude equation that I need to write down. And so when I write down this equation, the exact reformulation would have an equation here, and then I can relax this. If I relax this in this way, we've seen this before. This was Jeff Lindorff's ice cream cone. This is a second-order, rotated second-order cone. So this is a convex structure again. And it's a relatively small, it's a small cone. It only involves these 4 variables. So it's a 4-variable cone, and that relaxes this non-convex equation here. So I've done this reformulation. Now I have linear equations on the sort of for the power flow equations, and then this one set of cones that I have to write down. Okay, so this is quite nice. Second-order cones are easier to deal with than semi-definite programs, so you can solve these problems much more efficiently. But the relaxation is not as tight. So there's examples that show this. And in the last 2 minutes or so, I think I need to speed up a little bit. I was going to show you about GIC, something about GIC blocker placement. So this is a project we did at Argonne National Laboratory together with Los Alamos National Lab and Lawrence Berkeley National Lab. So we're interested in what happens if there's a big solar storm that induces a magnetic current and then forces these power lines to overload. And this is a really challenging problem. So first of all, you need to combine AC and DC power flow equations. So you model the traditional power grid with AC equations, and then you model the induced current from the GIC, from the geomagnetic induced current, using a DC power flow because it's fairly, it doesn't change much over large spaces. So you have the traditional challenges of non-convexity. There's a large scale. You need to introduce these transformers, which are non-smooth, and so this is a very challenging optimization problem. You can do something interesting here. You can look at different formulations. So you can compare polar and rectangular formulations and look at different sets of relaxations of solving non-convex problems. If you solve relaxations, you might not get the correct answer. If you solve non-convex problems, you might not get the correct answer. So, and then this is, we looked at this on 2 networks. That is EPRI-21 that I showed earlier, this small network, and then with 21 and UIUC 150, which is a sort of toy network that comes from the University of Illinois, Urbana-Champaign. There are the blocker locations. So the question here is, at which point in the network do I place my blockers? And so I have binary variables that place these blockers. But these blockers are basic grounding stations or transformers that take care of any geomagnetic induced currents. But they're very expensive. They're not cheap. And so you don't want to have too many of them. And then one of our postdocs coded this up in Julian Jump and got results. And it turns out that if you want to get exact solutions to the MINLP models, the solvers really need a long time. And so we timed out after 1 hour wall clock time. There was another solver that we got heuristic solutions, but reached time limits as well. And so we're now exploring other heuristics to solve this problem, where we're not looking at solving, where we're taking advantage of the fact that we can solve the power flow equations often very fast, but the optimization problem is much harder to solve. And this is just to show what happens if you don't install blockers. Then as you increase the magnitude of the electric fields, which is measured in volts per kilometer, from 5 to 20, there's a sort of cost involved with the load shedding. So you're losing customers basically because lines, you have to shut down lines. On the other hand, if you start installing blockers, the larger the magnetic field is, the more blockers you need, but you don't have any load shedding. And the E field, electric field that we looked at here, is sort of similar to an event that happened in 1989 that shut down the Hydro-Quebec distribution system. But still very small systems because these geomagnetic induced currents, they're not local to very small areas. They're really global across all of the United States, for example, or all of the planet. Okay, so I looked at two convex relaxations, show semi-definite relaxation, and the trick there is look for bilinear terms, form this matrix, this outer product matrix W, which is X transposed, that expresses every bilinear term now as a part of your matrix W, and then you can write all the constraints in terms of W. And you have a relaxation, if you relax this equality to an inequality. And Jaber's second order cone relaxation is sort of a little bit more intricate on how to get it. Both relaxations have examples that show that they're not exact. So this is not the panacea, but they help us at least to develop algorithms and think about these problems in terms of global convergence. And with that, I think I'll stop and see if there are questions. If not, we're going to switch. Yeah.
So when we are solving non-convex problems, because it is quite unsolvable and often it is intractable. So because we do not know the optimal solution, right? So when we are solving with relaxation, so possibly theoretically we can say the relaxed solution is suboptimal. But how much suboptimal it is, how we compare to solvers?
Right, so the question is if I have a non-convex problem that's really hard to solve, how do I know that my relaxation is far away or close to the solution of the true optimum? And so I can do two things, right? If I can find local solutions, like I do over here, and then I can compare this local solution to my global solution, and this would indicate that there's a large gap. I might do some multi-starts on the non-convex problem. I think it's really hard. I think if the non-convex problem is really hard, then finding this gap is not easy. But you can also often refine your relaxation. So you can, for example, if I thought the solution was here and I solved my relaxation and the solution is out there, then I would say, well, something is off. My relaxation is clearly a long way away from my true solution. So what I'm going to do then is I'm just going to split this problem in two. I'm just going to split it in half. And I'm going to say, well, the solution has to lie in one of those halves, right? Either this guy is right, or my relaxation is too far away, and this guy is close to the solution. That's the only two things that could happen. And so I now solve two problems, but now I can get a tighter relaxation. So once I do this, I might be able to get a relaxation that sort of over here is much tighter, and out here, well, maybe still quite big. And now I solve these two separate problems. So I went from solving one problem to having two problems. So I had one original problem, now I have two smaller problems. When I solve this problem, I'm going to find that my relaxation and my true solutions are quite close together. And when I solve this problem, I find that, well, I'm still far away from what I really have. And so I know that the solution will not lie in this area here. So, and this is called branch and bound. And so that's probably one approach on how to do this. So we don't just solve the relaxation and hope that we get a good answer, but we need to work on the relaxation, refine the relaxation, and make it better. And that's a sort of general framework for solving non-convex optimization problems in very broad terms. And we'll talk about this tomorrow. We'll start talking about that.